when observed results, like so you actually do your study, when observed results are unlikely under the assumption that the null hypothesis is true, we say that the result is statistically significant and we reject the null hypothesis. So this is the sort of thing we're looking for here, is for statistical significance, which allows us to reject the null hypothesis. Remember, in the language of hypothesis testing, we will never accept the null hypothesis. We will just reject one or the other. Reject or do not reject. So there's 2 to 3 to 4 different kinds of approaches to hypothesis testing. I like to talk about the classical approach, but we're actually going to use what's called the p-value approach, because the classical approach to hypothesis testing kind of turns it into what we've done before. In the classical approach, we just see if the sample statistic we get, so if the population proportion or the sample proportion, I guess I should say, is too many standard deviations from the population parameter. So like let's say it's more than 2 standard deviations away, we would reject the statement in the null hypothesis. So we're basically saying if it should be here and we're getting a value that is 2 standard deviations away from the typical population parameter, then we reject the null hypothesis. To be a little bit more precise, that's what it feels like, more precise to me, we will use what's called the p-value approach. A p-value is the probability of observing a sample statistic as extreme or more extreme than one observed under the assumption that the statement in the null hypothesis is true. The reason I bring this image up and the reason I wanted to talk about the classical approach is because look at all of these images. They look very similar, correct? It's the same concept of if it's too far away from what should be happening, we can reject the null hypothesis. Okay? We have to get more specific about how far is too far away, and that's where the p-value comes in. If the probability of getting a sample statistic as extreme or more extreme than one obtained is small under the assumption then the statement in the null hypothesis is true, then we reject the null hypothesis. Now, this ended up being really small when I printed it. I didn't realize this, but I need you guys to look at these underneath each of these images. There's an equation of some sort for the p-value for each type of test, a right-tailed, left-tailed, or two-tailed. I'll zoom in so we can maybe read it off of mine. But the first one says that in a two-tailed test, we will find the p-value by doing 2 times the probability that our z-score we're going to compute is greater than the absolute value of the z-score of the null hypothesis. So absolute value. That's the main idea here. If we're doing a left-tailed test, we're looking at the probability that our z-score is less than the z-score from the null hypothesis. And for a right-tailed test, we've switched that to a greater than, which makes sense because it's greater than. Okay, so basically what we're trying to figure out is, would it be unusual to obtain a sample proportion of p hat, some value, or higher from a population whose proportion is known? Okay. How small should we make the p-value to reject the statement in the null hypothesis? It depends on the situation and the consequences of making a type 1 error. If the consequences are high, we're going to have to use a different kind of p-value than if it's just like a whatever consequence of being wrong and making a type 1 error. The bottom line is this: the lower the p-value, the stronger the evidence against the statement in the null hypothesis. So the lower the p-value we get, the stronger the evidence is against the statement in the null hypothesis, because that means that it is more unlikely that we will get this sample statistic when a population proportion is something else. So the population proportion is probably wrong. This table here is very helpful. It tells you the different kind of p-values you can get and what we should conclude. The main 2 things I need you to know is that if you get either of these top 2 options, we do not reject H naught. But if we get any of these bottom three, we're going to reject H naught. So that will help you draw your conclusion sentences. It's the type of evidence, strong, some, moderate, or none, or very strong evidence against the null hypothesis with these different p-values. So it's saying if you get a p-value that's greater than 0.1, do not reject. If you get a p-value between 5 and 10, there's some evidence but not enough to reject, because again, this is 5%. We've used 5% as our unusual for the entire course. If it's less than 5%, we're going to start to reject it. Between 1 and 5%, it's a moderate amount of evidence. Between 0.1 and 1%, that's strong evidence. And less than 0.1% is very strong evidence against the null hypothesis. So what are we actually going to calculate here to get the p-value? That's a great question. We're going to follow the 5 steps in this main idea box. And we will do these 5 steps over and over and over again today. We're going to determine the null and the alternative hypothesis, which is what we practiced last class in writing those statements. It says to select a level of significance. The problem will tell you the level of significance. If we have a random independent sampling with an appropriate sample size, we will continue with steps 3, 4, and 5. Step 3 is going to have us evaluate or find what's called the test statistic. And we're going to use the standard normal table to find the p-value. And just so you know, the standard normal table, that's your pink table for my class this year. But the test statistic that we're going to use is this Z naught right here. So I'd put a little cloud around this guy maybe. This is what we are computing specifically for population proportion to run a hypothesis test on population proportion. After we get this Z naught, we're going to compare the p-value with the test statistic. If the p-value we get is less than the significance level that we are choosing, we will reject the null hypothesis. Or we look at that table on the other page. And then, of course, we put it back in words and we state the conclusion. There is a formula for this on our calculator. However, we're going to do all of these by hand so you can follow the steps on the calculator. Your homework's going to ask you to do it by hand, though, and we do get different numbers when we do this by hand than when we use technology. So unless the question specifically says to use a calculator to do it, assume you're doing it by hand. So let's hop right into it. Let's see one of these things from start to finish. Humira is a medication used to treat rheumatoid arthritis. In clinical trials of Humira, 705 subjects diagnosed with rheumatoid arthritis were administered 40 milligrams of Humira every other week. Of the 705 subjects, 66 reported nausea as a side effect. It is known that the proportion of RA subjects in similar studies receiving a placebo who reported nausea as a side effect is 0.08. Does the sample evidence represent significant evidence that a higher proportion of subjects receiving Humira experience nausea as a side effect than those taking a placebo? Use the 0.05 level of significance. So we start at the beginning. We have to first state our null hypothesis and our alternative hypothesis. Remember, in math sentences, so not actual words, the H naught is always an equal sign. So for us, we're saying that the equal sign here, the population typically has 0.08 of the population reporting that they get nausea. This is from the placebo. We want to know specifically, does our Humira study represent significant evidence that a higher proportion of subjects receiving Humira experience nausea? So is this going to be a right-tailed or a left-tailed test? Are we going greater or less than? Greater, which means it is a right-tailed test. So we're checking P1 to be P greater than or equal to, greater than 0.08. Our population proportion is typically 0.08. We're trying to see if this sample that we got of Humira patients is statistically significant. Step 2 says select alpha and verify the sampling. So what is the alpha they told us to use? 0.05, which is a typical level of significance for a hypothesis test, by the way. We're going to check the 3 things it requires for us to do these sort of tests. We need it to be done random. Do we see that this is a random study? I don't know if it actually even says that, but we're going to assume that it is randomly sampled. Typically, you'll see that in the words. Then we need to check the sample size to make sure it's large enough compared to the population. So we look at n times p naught times 1 minus p naught, which would be 705 times the 0.08 from the population from the null hypothesis times 1 minus 0.08. In your calculators real quick, I took the population size n, multiplied it by the p from my h naught, and 1 minus p from my h naught. What do you get? Yeah, 51.88. Is that bigger than or equal to 10? Yeah, don't think too hard about that. That's good. We needed that number to be bigger than or equal to 10. That's been the formula we've used all class to determine sample size. That's big enough. Then we need to check independence, and we do that by making sure that the sample size, while it was large enough in that first one, we need to see that it's smaller than the population. We are studying people with rheumatoid arthritis. Do we think that there are way more than 705 subjects in the world with rheumatoid arthritis? Yeah, we're pretty sure that we're good with this population. In fact, there are 150,000 RA patients in the US alone, so 705 is definitely small enough that we can assume independence here because it's less than 5% of the population. So boom, 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 check, 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 we're good. Now we go into the calculations. We're going to find our test statistic Z naught. We need to find our p hat from the study. So p hat is the number of successes we see out of the population, meaning out of the 705 from my study, how many had nausea? 66. So if I was calculating this, 66 out of 705 as a decimal. We'll just round that to 0.094. Okay, that's p hat. That is the proportion of our population we studied that had nausea. To find our test statistic, we use the formula from the top of the page that I've copied down here for you so you can see where it's coming from. We will take p hat, that's the number we just found, 0.094, and we will subtract p naught, which was the 8% of the population that had nausea from the placebo. We're going to divide that by the square root of, I need a bigger square root, p naught, which is 0.08, times 1 minus 0.08, divided by the sample size, which was 705. I do recommend, especially on my calculators, to use the fancy fraction twice here. So fancy fraction, type the numerator, go to the denominator, do the square root. Inside the square root, do the fancy fraction again. So it is a little bit complicated to type in. I'll give you a second. It should be 1.37. And since this is a z-score, we do keep 2 decimals. Z-scores are read off of your pink table. So our p-value is the probability that our sample statistic would be greater than Z naught. So we need to know the value of, from the table, the probability, the area under the curve when the p-value is 1.37. That sounds better. But this is a right-tailed. Does that table tell you on the right side or on the area on the left side? Let me hold mine up so you can see what I mean. You guys actually did teach me that. I went and verified with some other stats teachers if this was a thing. I did not realize this because no one had brought it to my attention. This peak table always shows you to the left. Let's look at the picture at the top. It's areas on the left. Yeah. Do we want an area on the left right now? No. We're wanting area on the right because that says greater than. Yeah. So if I find 1.3 and then go over to 7. Oh. Gabby, what was the number you said? I can't see upside down. Hold on. 0.91. 0.914666. Great. That's the area on the left. How would you find the area on the right?
Yeah.
It says it on the homework.
Oh, see, I didn't read that part. Y'all taught me something.
Yay.
Oh, so cool. So what is that area when you flip this over?
To the negative?
Mm-hmm. Because this is now it's to the right.
0.8534.
0.08534. I didn't hear you, Amelia. I'm sorry. So remember, again, visually, we're finding this direction, the right side, 1.37. So on your table, you can flip it over so that you are looking at the left side of negative 1.37. Okay, once we get this p-value, we have it. This is what we were wanting this whole time. We had our sample statistic, which was 1.37. That's our z-value we got here. We got our p-value. This is great. We need to compare the p-value to the level of significance. So here's what I'm going to do. I'm going to write, we're going to write an inequality, but I'm not going to put the inequality sign there yet. You guys told me our level of significance is 0.05. Which number is bigger? So that means that our inequality sign says that our p-value, our p-value is greater than our level of significance. If our p-value is greater than our level of significance, that means that there's only moderately unusual or no sort of evidence at all. So our conclusion is that there is not sufficient evidence at the 0.05 level of significance to conclude that the proportion of subjects taking Humira who experience nausea is greater than 0.08. If that inequality sign had gone the other way and our p-value was less than the level of significance, we would say there was significant evidence and we would reject H naught. We just do not reject H naught. Questions about this process? Don't let me miss lunch because the bells aren't ringing for AP tests, FYI. 43 is what we're looking for if you don't know that number. You made me think for a second. Okay, let's just try this again. So we're going to do this whole process for another study. This is the process for hypothesis testing for population proportion. Here's the question. It says, which do you think is easier to raise, a boy or a girl? When asked this question in 1947, 24% of all Americans said raising a girl was easier. In June 2018, the Gallup organization surveyed 1,500 adult Americans, of which 408 felt it was easier to raise a girl. Does this result suggest the proportion of adult Americans who believe it is easier to raise a girl has changed since 1947? We start by stating the null and the alternative hypothesis. Remember, the null hypothesis is always an equal sign. So what was the proportion of the population that we knew about in 1947 that thought raising a girl was easier? 24%, so 0.24. That is the norm. That is what we knew in 1947. We are checking to see if the proportion of adult Americans who believe it is easier to raise a girl has changed. Is this going to be a right-tailed, left-tailed, or two-tailed test? We're trying to see if it's changed at all. I don't care if it's bigger or lower. We just want to see if it's not equal, which means this is a two-tailed test to see if it's not equal to 0.24. Since they didn't particularly tell us what the level of significance would be, we're going to choose the pretty basic option of 0.05 because also it's not super bad if we get this wrong. It's not going to like cause us to lose a ton of money. It's just a question that we have. We have nothing writing on the line for us making that type 1 error. Let's check our 3 things. Did we randomly survey these Americans? We did. The Gallup organization is a surveying company that does random sampling. Just FYI. That's actually something you'll see in media a lot, is that Gallup organization did it. Now we check the sample size. What are we multiplying here?
The sample size?
What is our sample size? No, that would be our proportion of the population. What's our sample size from when we did the study in 2018? 1,500. We checked 1,500 people, so that's our sample size. P naught comes from the null hypothesis, and then 1 minus P naught again from the null hypothesis. In your calculators, please calculate what 1,500 times 0.24 times 1 minus 0.24 would give you. And as long as it's bigger than 10, we're good.
273.6.
Yeah, that's 273. I lost the number in my head. 0.6. That's obviously greater than 10, yes? We're good. Now we check independence by making sure our population is less than 5% than the overall population. We're studying the adult Americans. We've been over this before. How many adult Americans are there?
A lot.
A lot. Is 1,500 going to be less than 5% of all adult Americans? Yeah. So our population size is fine. The U.S. population is huge. Okay, boom, boom, boom. Check, check, check. We're ready. We're set up. We can actually find this test statistic. From the study that we're looking at in 2018, from the Gallup study, how many people thought raising a girl would be easier?
408.
408 out of the number that we surveyed, which was 1,500. 408 out of 1,500, round to 3 decimals, please. Yes. It sure is time for lunch. Thank you, Brooklyn. Okay, after lunch, we'll finish this problem. All right, so before we left for lunch, we were on step 3, which is finding the test statistic. All we had found so far was p hat, and we need p hat to find the test statistic. So let's go ahead and find that. So z naught is what we're looking for. We have all of these values, though. So we'd use p hat, which is 0.272, and we're going to subtract P naught, which from the top, that's a hypothesis proportion, 0.24. All divided by the square root of 0.24 times 1 minus 0.24 over the population size, which was 1,500. Or sample size, sorry, I said population size. Sample size. So we calculate. Round to 2 decimals since this is a z-score. Bless you, by the way. 2.90. Nice. All right, so we have our test statistic. That's great. Now the test statistic is what we're going to use to run our p-value. Now I wrote out the formula of why you use 2 times the absolute value. It doesn't really matter as long as you can see that we are doing 2 times the probability that z is greater than 2.9. So on your table, let's find the probability that z is greater than 2.9. So go to 2.9 on your z table. Notice we're doing greater though, so flip it over to the negative side, negative 2.9. So we're doing 2 times 0.00187. We got this number from your pink table. And we would get 0.0038. That is our p-value.
Miss, I got 3 something.
What's the decimal after that?
I got 0.0037.
I don't have a calculator over here. 18.7 times 2. Did everybody else also get that? Very interesting. Okay. You're right. Let's try that again, Miss Quigley. 0.00374, yes?
Yes.
That sounds better. So sorry. Okay, once we have the p-value, we can compare the p-value to alpha. So I like to write both of them down and then just write myself a cute little inequality sign. So we have our p-value 0.00374. And then our alpha, our level significance, is 0.05. Which one is bigger? 0.05. So this time, since our p-value is less than 0.05, that means, our conclusion is, that there is sufficient evidence at the 0.05 level of significance to conclude that the proportions of, and then here's a typo I made because I just copy-pasted it. Oops. The proportion of adult Americans who believe it is easier to raise a girl has changed since 1947. So again, our p-value this time was less than our level of significance. It, that doesn't look like the word it, but it sure is supposed to be. In the problem before this, the p-value was bigger than our level of significance, so we did not reject the null hypothesis. Here, the p-value is less than the level of significance, so we do reject the p-value. We do reject the null hypothesis. Ready for the next one?
No.
So what happens if the sampling proportion is not big enough? Like, what if our sample size is not big enough?
What stuff happens
In 6.2, we used what was called the binomial probability formula, and we're going to bring that back to identify these unusual events. So in this example we're going to have too small of a sample size to assume normality, to assume that the sample size is large enough that it eventually becomes normal. So we're going to have to do something else. And we're going to use the calculator for a binomial probability situation to do this. Example 3, according to the USDA, 48.9% of males aged 20 to 39 years consume the recommended daily requirement of calcium after an aggressive Got Milk advertising campaign. Do y'all know what the Got Milk advertising campaign is?
Yeah.
Okay, this was like a big deal when I was a child. Every billboard, every commercial break, they really, really pushed us to drink milk because milk has a lot of healthy things for it. So it's a huge campaign in the early aughts in the 90s. The USDA conducts a survey of 35 randomly selected males aged 20 to 39 and finds that 21 of them consume the recommended daily allowance of calcium. At the 0.10 level of significance, is there evidence to conclude that the percentage of males aged 20 to 39 who consume the RDA of calcium has increased? Let's start right off the bat. What is our H naught? 48.9%. So 0.489. What are we trying to study here? not changed, specifically increased, which means this is going to be a right-tailed test. P greater than 0.489. Tells us to use the 0.10 level of significance. So we check random sampling. Do we randomly select these males? We do, so we're good. We check the sample size. How many people did we survey? 35. So we do 35 times 0.489 multiplied by 1 minus 0.489. Let me make that look better. Oh, that's not what I want.
8.7.
I don't know what's happening here on my, I don't know how that turned yellow if I'm being honest. What do we get here?
8.76.
8.76. Is that bigger than or equal to 10? No. So here's where this is a problem. Because this sample size is not large enough to assume that it is approximately normal, we cannot do what we did in the problems before. We don't even need to check independence because we don't have normality. So let's write a note to ourselves what this means. So this is not approximately normal. Use the binomial probability formula. This is where we are going to use our calculator to do this because our calculator has a function to do the binomial probability formula in like 3 clicks of a button, where doing this by hand takes us like a whole Excel spreadsheet. So we're going to compute the p-value using the calculator because we can still find a p-value. It's just going to be done by a different method. We still need p-hat. Of our tiny little survey, how many said that they have the RDA of calcium? How many people said yes, they have the recommended daily amount of calcium? 21 out of our 35, which is 0.6 of that sample. Because binomial probability is only really found in our calculator for x less than or equal to some particular number, we had to do the following math. The number we had binomially was 21 successes. We're trying to see if our random variable, what the probability our random variable would be above 21. Well, we know that we can only find this with less thans, so I immediately change it to the 1 minus. Do we see? But because, again, we can only use less than or equal to, and this says less than, we have to change it 1 less than that, so it's less than or equal to 20, instead of just straight up less than 21, because our calculator only does less than or equal to. So what numbers are less than 21? 20 and under. So let me do that again. Back up a little second. So we know this is what we're looking for the 21 successes. Probability doesn't work this way, so we do 1 minus less than. But a binomial only does less than or equal to. So what is less than 21? 20 or under. So we have to switch it to those numbers. But here we go. We're going to use our calculators for this one. Press second, and then the button that says VARS. We are specifically doing this second option. So we are looking for binomial CDF. CDF, as opposed to PDF, CDF. After we do this, we're going to enter the number of trials, 35, and the probability of successes, and the number of successes, and hit enter. I'll get on my actual calculator here on my computer in a second, because I don't think my online one tells me. So again, we use the binomial CDF. It should say binomial CDF 35, 0.489, 20. Might be helpful to write this down so you can see what your calculator should say. So right here, maybe like put a little note to yourself that this should say, it's up. Oh, you're right. You can't see. I'm showing my calculator. binom CDF 35.48920. And what did our calculators tell us again?
0.873.
So we do 1 minus 0.8739. And what do we get? .1261?
Yes.
Fabulous. So that is our p-value. We had to do this differently because we didn't have normality. We didn't have a sample size large enough to assume that it's approximately normal. But then we go back to how we solve the other ones. We compare the p-value to alpha. The p-value we got was 0.1261, and we're comparing that to alpha, which was 0.10. Which one's larger? The p-value, correct? If the p-value is larger than the level of significance, then there is not sufficient evidence at that level of significance to conclude that the proportion of 20 to 39-year-old males who consume the recommended daily allowance of calcium has increased. So p-value above level of significance, not enough evidence. P-value less than the level of significance, we do have enough evidence. Now, I need to be clear to you, because this will get confusing next class. This is for population proportions.
Okay.
There's different steps for other measures of samples. So next time we're going to learn about mean. There's a different one even for standard deviation that we're not going to get into.
We don't have time.
We don't have time. Nor did we cover it in the last chapters.